This is a debriefing on 3-point charges homework assigned to Physics CP on January 11th, 2021. Problem 1. Q1 is 925 protons, Q2 is 865 electrons, Q3 is 335 protons. Distance from 1 to 2 is 25 millimeters, from 2 to 3 is 10 millimeters. Calculate the net force acting on charge 2. So a little bit of a sketch wouldn't hurt, and then labeling what's going on. 925 protons, and then arbitrarily I'll say here's Q2. In the middle, 865 electrons, and then a shorter distance to right to some sort of scale, Q3. Q3 is 335 protons, and the task was to calculate the net charge on the middle charge, Q2. All right, well, of course, we're going to be using Coulomb's law. F is equal to K, Q1, Q2 over R from 1 to 2 squared is the general formula. One thing we have to do is convert protons to coulombs of charge and electrons to coulombs of charge. Well, the charge on one proton is 1.602 times 10 to the negative 19th coulombs. So if we multiply the number of protons times the charge in coulombs per proton, we will convert the charge into units of coulombs. I'm going to do that on my calculator just as I enter the numbers, since I've already stored this number in my calculator memory. I've also stored this number in my calculator memory. So it becomes a little bit easier to just say, let me straighten things out here. To calculate the net force on the middle charge, I see that this is positive, this is negative, this is positive. So there's going to be an attraction pulling Q2 to the left. There's also going to be an attraction pulling Q2 to the right. So after I calculate the strength of the forces between this pair and that pair, I have to take the difference between them. Whichever one is the stronger force will be the direction of the net force. All right, so F between 1 and 2 is K times Q1 times Q2 over R12 squared. And into my calculator, that means I type in K times 925, and I'll use this the stored letter P to represent the charge on a proton, times 865, and if you like, really, you should put in the minus sign if you can't reason this out and keep track of it yourself. So a minus sign to represent the negative charge of an electron, times 865 times the charge on one proton, and I'm going to divide that by distance. It says 25 millimeters, but of course I have to work in units of meters. So I have to move the decimal point 3 places to the left, and this is 0.025 meters, quantity squared. All right, well, Boltzmann's constant K times 925 protons times 865 electrons divided by 25 millimeters squared. Now, I didn't bother with the minus key because I already figured out that this is the magnitude of the force that's going to be pointing to the left in this situation. So here it is, 2.95 times 10 to the negative 19th power newtons to the left. And I didn't bother saying, oh, that's what that minus sign means. In this case, it's attracting it, it's pulling it Now I calculate the force of attraction between Q2 and Q3. Well, between Q2 and Q3, it's going to be K times Q2, which is 865. I'll put the symbol for proton, even though these are electrons. So if you want to be proper, you can put a minus sign in front of all this, times 335 protons divided by the distance between them is 10 millimeters. Well, there's 1,000 millimeters in a meter, so I have to move the decimal point 3 places to the left, and make sure you move it 3 places to the left. 10 millimeters is 1 centimeter is 1/100th of a meter. And by the way, the zeros after the 1 are significant digits. So this is expressed to 3 sig figs. So properly, you shouldn't just write 0.01. Properly, you should write 0.0100. And into the calculator it goes. So alpha K times 865, alpha P, which is where I've stored the charge on the proton, 335 alpha P divided by 0.01 squared, enter. That says this one is 6.69 times 10 to the negative 19th power newtons. Now I've already figured out that this is going to be attracting it to the right. So I'm just going to write it to the right. And now, fortunately, they're to the same exponent, so it makes it easy to compare and ask yourself, which one is the greater force? 3 to the left or almost 7 to the right? Well, this is larger than that number. So this is the one that's going to be the direction of the net force. So the net force on Q2 is, and now take the difference. In fact, it's going to be times 10 to the negative 19th power. So you could just say, ask yourself, what is 6.69 minus 2.95? And the calculator says, oh, that's 3.74. So there you have it, 3.74 times 10 to the negative 19th power newtons to the right. Number 2, the problem reads, Q1 is now 2.14 millicoulombs, Q2 is now 4.23 microcoulombs. That's actually a mistake. I meant for that to be milli, but oh well, micro. And Q3 is negative 5.24 millicoulombs. The distance between 1 and 2 is 16 centimeters, 2 to 3 is 28 centimeters. Calculate the net force acting on charge Q3. Okay, so do a little sketch and annotate it with the information. I'm always putting Q1 on the left, and it says this is 2.14 millicoulombs. And then I go a distance, we'll call this 16 centimeters, and 0.0, by the way. So everything is provided to you to 3 sig figs. Q2 is 4.23 microcoulombs. Then I go another 28 centimeters to the right from that, and I get to charge Q3, which is negative 5.24 millicoulombs. And I ask you to calculate the net force on charge Q3. Okay, so let's just look at the algebraic signs of things. Q1 is positively charged. Q2 is also positively charged, and Q3 is negatively charged. So Q1 is going to be pulling Q3 to the left. Q2 is also going to be pulling Q3 to the left. So therefore, when I calculate the magnitude of the forces acting on Q3, when I get done, I add them together because they're both going to the left. and I say, this is the net force acting on Q3 to the left. All right, so the force between Q1 and Q3, in this problem, I don't care about the force between Q1 and Q2. The force between Q1 and Q3 is K times 2.14 millicoulombs times, yes, there's a minus sign if you want to put it there, 5.24 millicoulombs. And now you have to divide it by the distance from 1 to 3. Well, first we go 16 centimeters, then we go an additional 28 centimeters. So really, we're doing 16 plus 28, which I can't do in my head anymore, which is 44 centimeters, which I can still convert to meters by dividing by 100. At least I can do that one in my head. And say the distance between Q1 and Q3 is 0.44 meters. Milli, of course, means times 10 to the negative 3. So on my calculator, I would type in alpha K 2.14 times 10 to the negative 3 times, yes, I should put in the minus key to keep you happy, 5.24 times 10 to the negative third power divided by 0.44 meters squared, enter, and it says I have an attractive force of 521 kilonewtons. So 521 kilonewtons to the left. And yes, you should be able to look at a number and pretty much instantly use a Greek prefix that says, oh, this is 527,714.7136. To 3 sig figs, I move the decimal point 3 places to the left. 3 places to the left is a Greek prefix that means kilo, and this rounds off to 521,000 newtons, 521 kilonewtons. Now I calculate the force between charge Q2 and Q3. This is going to be K. The magnitude of charge 2 is a very tiny 4.23 microcoulombs. Micro means 10 to the negative 6. Again, with the exchange key, 5.24 millicoulombs. And now, what is the distance between Q2 and Q3? It's just 28 centimeters, which is 0.280 meters, quantity squared. All right, well, so I get alpha K times 4.23 times 10 to the negative 6 times the exchange key times 5.24 times 10 to the negative 3, and I see I typed in 3 instead of 6 here. So fix that. Divide by 0.28 squared. I get an attractive force of 2.54 kilonewtons. So 2.54 kilonewtons also to the left. All right, well, they're both pointing to the left. So to get the total net force, I'm adding these two forces together, and I could say that the net force on Q3 is 1 plus 3 is 4. So this rounds off to 3 sig figs as 524 kilonewtons to the left. The 4 isn't significant because we don't know if that's a 0.004 out here. In fact, it is probably is not. The 5 is not significant, so I'm rounding this up to the nearest whole kilonewton. This is 3. 1 plus 3 is 4. Now, you may have rounded it differently, and if you rounded it differently, you would end up with 523 kilonewtons, possibly. That is still considered correct answer. So, technically speaking, you're supposed to round off every step of the way. But if you left this in your calculator and you left this in your calculator and just added them together and then rounded off at the end, I won't punish you for doing it that way because I'm often very lazy and that's how I do it myself. Just be aware, technically the rule is you round off each calculation according to the correct number of sig figs for that particular calculation. All right, problem number 3. Q1 is, well, you can kind of read it yourself. Q1 is negative 1.5 coulombs, Q2 is negative 2.5 coulombs, Q3 is negative 1.8 coulombs, distance from 1 to 2 is 1.9 meters, from 2 to 3 is 2.1, that should have been with 3 sig figs, 2.10 meters. Find the net force on the left guy. As always, it really helps if you do a sketch and label what's going on as you look at your sketch. So Q1 is negative 1.50 coulombs. Then I go a distance of about 1.9 meters. Well, a distance of 1.9 meters to get to Q2. Q2 has a charge of negative 2.5, and that should have been 3 sig figs as well. Oh well, coulombs. So because of the way I wrote it 3 different times, this problem should be solved to just 2 sig figs. Oh well. Then you go an additional 2.1 meters to get to Q3. And when you get there, Q3 is negative 1.8 coulombs. And in this problem, I ask you to solve for the net force on Q1. Q1 is negatively charged. Q2 is negatively charged. Q3 is negatively charged. Like charges repel. So the electrical force between 1 and 2 is going to push 1 to the left. The electrical force between 1 and 3 is also going to push 1 to the left. So I'm going to calculate the magnitude of the electrical forces for each of those 2 pairs and then add them together and say, oh, the net force is strictly to the left. Here we go. The force between 1 and 2 is going to be K times, and since it's a negative times a negative, it's a positive. The 2 minus signs are going to cancel. So I'm not going to bother typing them in. 1.5 coulombs times 2.5 coulombs divided by 1.9 meters squared. All right, let's see what the calculator says for that. Alpha K times 1.5 times 2.5 divided by 1.9 squared, enter, and it shows a huge number. All right, well, I should almost switch to engineering notation to make it easier for me. Otherwise, you have to count. Oh boy, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 3.34 times 10 to the 9th power. 9.34. Now there is a Greek prefix that means 10 to the 9th power. That's giga. Giga is a billion. A billion is 10 to the 9th. A gigabyte of memory on your memory stick is a billion bytes of memory. So giganewtons, of course, to the left. Now I shut off charge Q2, turn on charge Q3, and the force acting on charge 1 caused by Q3 is going to be K times 1.5 coulombs times 1.8 coulombs divided by the distance from 1 to 3. All right, well, so I believe that's 3.7 meters squared. 1.8, 2.8, 3.8, 3.7. Yeah, okay. So alpha k, very convenient to have it stored in memory, isn't it? 1.5 times 1.8 divided by 3.7 squared. And you might notice I don't even bother having a multiplication sign between the k and the value of q1. That's because a TI calculator understands it's implied that you're multiplying k times the number that comes after it. All right, just one less step to get to the answer. And you can see it's got the same number of digits as the previous answer. So this is going to be 1.77 giganewtons to the left. 1.77 giganewtons to the left. So to find the net force, you just add these two magnitudes together. And you would write the net force on Q1 is, oh man, 7 plus 4 is 11. 10 plus 1 is 11. 9, 10, 11 giganewtons. And this becomes insignificant to 3 sig figs. Actually, that's not true. This result would be to 4 sig figs. However, our calculations were only done to 2 sig figs for some of these numbers, like the distance or charge. So really, I'm going to round my answer off in the end is 11 giganewtons to the left. Ta-da! This concludes my debrief on 3-point charges homework. And I see here when I wrote the answer key, I should have rounded to 2 sig figs. Great. Well, I do see belatedly I made a mathematical error on the last problem. I see that the distance between Q1 and Q2 was 1.90 meters, and the distance from Q2 to Q3 was 2.1 meters. And when you add those together, you do not get 3.7 meters, which is what I used in my debriefing. You get a value of 4 meters. So I typed in the wrong value, and that's going to reduce this 1.77 giganewtons. So let me recalculate it using 4 meters of separation instead of 3.7 meters of separation. Alpha k times 1.5 times 2.5 divided by 4 meters squared reduces the force between 3 and 2 down to 2.11 giganewtons. That sounds wrong. So I'm putting in wrong values all over the place. Q3 has a value of 1.8 coulombs, but I typed in 2.5 coulombs here, so that's still a mistake. And the reason I recognize it's a mistake is because as the distance increases from 3.7 meters to 4 meters, the magnitude of the net force should go down. And when I looked at these two numbers, I said, hey, wait a minute, this went up, not down. I've made a mistake. So let's try it a third time. K times 1.5 times 1.8 divided by 4 squared, enter. And now I believe I'm looking at the correct number. This is 1.52 giganewtons. So instead of 1.77 giganewtons, it's 1.52 giganewtons. Well, still, I should only have done this to 2 sig figs anyways. So 5 plus 3 is 8. and 9 plus 1 is 10. So interestingly enough, 10.8 giganewtons to the left would be a reasonable answer on your homework problem. All right, there you go.